Hello, I'm here to do this. I might not actually say all of these things, but maybe some of them. Okay, this is joint with Josh, who is here, Alekos, who is not here, Zoltán, who is not here, and also some other part with Suman, who is not here. Okay. Okay, so let me just set some things up. So every okay, so maybe fix every group is countable and discrete because I only know how to do that. So fix a countable discrete group. Because
you don't know topology.
Because I don't know topology.
You said you don't know topology.
I don't know topology if there's also a group operation at the same time. Yeah, but I have to know topology for this, or it's going to be a big problem. So fix a countable discrete group gamma, and actually the gamma might only ever be a free group today. So okay, but it could be infinitely generated because that's the point. Okay, so this is a general Polish space fact. Every compact Polish space embeds is a closed subspace space of the Hilbert cube of this is the Hilbert cube. It's countably many products of the interval. So every action, continuous action, every action will be continuous today. So every continuous action of gamma on a compact Polish space, also everything will be Polish. Compact Polish space embeds as a closed, that's what's called a subshift. It's a closed gamma invariant subset of 0, 1 to the n. So it's the shift of gamma with this alphabet. Okay. So my motivation is that I want to look at every action of gamma on every compact Polish space. But that's just the same as saying I'm just looking at closed gamma invariant subsets of this one thing, which is sort of, it's all in one place. Yeah, and initially the motivation is to look at equivalence, arbitrary countable Borel equivalence relations, and see which ones arise as these things. But I might not talk about that so much. Okay, well, we'll see. Okay, so the thing in descriptive set theory is that this is a compact space, and then this is the collection of all compact subsets. So this is actually a Polish space. So maybe I'll give some notation. So denote by, I actually don't remember what notation we used. Let's just say the shifts. Let's say, okay, I'm just gonna do it. So this is, I should probably fix a letter for the Hilbert space, but it's too late. Okay, so denote by this the Polish space of these things, closed gamma invariant subsets. So it's because they're subshifts. That's what the SH is. Subsets of 0, 1 to the n to the gamma, and then this is with the Viatorist topology, like the restriction of it to this subspace. It's symmetric, it's just house stroke distance. Okay, so I'm going to be working on the space, and what I'm concerned about is if I take a property of actions or equivalence relations, what sort of subsets do I get? So for example, I'm interested in maybe how big are the subsets or how complicated are the subsets. Okay, so this is the general theme of the talk. Okay, so maybe just because it hasn't been defined, or it has, but it hasn't, I'll define it again. So a countable Borel equivalence relation is hyperfinite. So it has, but it hasn't. So whatever I said last week, it's that, but it's even more that. Okay, it's hyperfinite. A countable Borel. This is just you can just think of it as you just take the orbit equivalence relation of any of these things. It's hyperfinite if E is the increasing union of a bunch of finite equivalence relations, and there's no measures, so it's E on a standard Borel space X. So I'm not allowed to throw away a measure zero set because I don't even know what a measure is. So it's hyperfinite if it's the increasing union of finite Borel equivalence relations. So if if there's an equivalence relation where F0 is contained in F1 is contained in F2, and so on and so forth. And these are finite Borel equivalence relations. Finite meaning not the set is finite, but every class is finite. So okay, so just so you like have a concrete idea in your head, if you take any action of a locally finite group, so any action of a locally finite group, because it's an increasing union of finite groups, right? So okay, so the important thing is that I'm not allowed to throw away a set of measure 0. Okay, but now I will define throwing away a set of measure 0. So okay, so given a Borel probability measure mu on some space X, let's see, E on X is mu hyperfinite, which came up last talk, maybe. Mu hyperfinite, if it is hyperfinite on a set of measure 0, which is the one that you all know and love.
The other way around.
Oh, I said it's on the measure 0 set? Oh, that's wild. Okay, it's hyperfinite if there's a conal set, a mu conal set Y, such that E restricted to Y is hyperfinite. Okay, and then since I don't want to fix a measure because I'm not a measure group theorist, or I am, yeah. So I'm a descriptive set theorist, right? So I'm going to allow myself to vary the measure. So I need the following. So E on X is measure hyperfinite if it's mu hyperfinite for every mu. If E is mu hyperfinite for every Borel probability measure mu. Yeah, okay, so one thing I am concerned about, I guess, is if you take the set of all actions. Oh yeah, so maybe I should have said this. So I'm interested in actions of like an arbitrary, like a fixed countable group, but I'm also interested in all countable groups like simultaneously. But any action of a countable group is just an action of F infinity, right? So because you know F infinity projects onto every group. So yeah, so that's why I said they'll probably just be free groups. Okay, so here's a fact. I guess it's a theorem. So here's a theorem: is that the set of, I don't know what letter I should use. The set of X in, so the set of things which are measure hyperfinite. Oh yeah, so I guess like a subshift, maybe X is bad. Okay, let's say call S. A subshift, okay, an element S of this shift space. So this space of closed subshifts is, you know, any of these properties has like property P if the equivalence relation does, if its orbit equivalence relation does. So, you know, I'll say like a shift is hyperfinite. What I mean is that the equivalence relation is hyperfinite and so on. Okay, so the theorem is that if you take, well, here's a theorem. Okay, so if you take the set of shifts, so the set of subshifts which are where S is measure hyperfinite. So this is co-meager. So yeah, so I guess one thing, maybe the only thing I'll be concerned with today, because the other thing is complexity, which I don't want to explain that much, maybe. So yeah, so I'm interested in co-meagerness. So co-meager is like the topological version of measure 1. So this space is a Polish space, so it already comes with the topology. So, and I want to say most things here are measure hyperfinite, and this says that. Oh, I guess I need like some quantifier. Let's just say where gamma is a free group. Is a free group. So what I actually need is that it's an exact group, because I mean, yeah, because a group having like this set being non-empty, you need, there's some groups for which this is just empty. That's there's these things called exact groups. The group is exact if it admits an immutable action on a compact space. So free groups are that. So, and I only care about free groups. Okay.
But I mean, you can always look at the fixed point there, right?
Yeah, you can look at fixed point. That's true, but wait, what do you mean?
Like when you have a constant function, there is a closed subshift.
Yeah, that's true. Yeah, I guess the construction I'm thinking of to get the comedianness. Yeah, I guess it won't be. The next thing I write will be empty, and then I'll need that to do this. Yeah.
I mean, can you add that they're also free in the theorem?
Yeah, so I'm actually that's gonna be the actual theorem.
Oh,
Yeah. So the actual theorem is this. So from which this follows. Okay. But anyways, I only know free groups. So okay, so the actual thing is this, which is kind of much funnier, I think. So if you take the things which are so S is free. So when I say free, I mean the action is free. So it's not a proper even equivalence relation. It's an action and measure hyperfinite. So this is actually a dense G delta, which is pretty funny. And then this is how you show. So it's a subset of this. So I guess it's funny because it's G delta, but the quantifiers here are crazy, right? It's I'm saying like for every Borel probability measure. Yeah, and okay, so let me just tell you why this is true. So this is true because of the following fact. Oh, so okay, so this set being non-empty is literally the definition of exact group. Okay, so I need it for this fact. Okay, and this follows from the following descriptive set theory theorem, which I'm sure you like. So this is a theorem, but not through us. This is Kechris-Louveau-Wooden. And okay, so this is a statement about sigma ideals of compact sets. So a sigma ideal is it's a set of sets which is closed downwards, and it's closed under countable unions. So if you have a measure, the set of measure zero sets is a sigma ideal. And sort of in this context, you can also talk about sigma ideals. And what I mean, so if you take a countable union of compact sets, it's not compact, right? So I'm just saying, if you take a countable union of compact sets and it is compact, then the thing is there. And also a subset of a compact set isn't compact, right? But I'm saying if you take a compact thing and you have a subset which is compact, then it should be in the sigma ideal. Okay, so, and I won't be too precise about it because I mean, it's also like not exactly this theorem, but it's the exact same proof. So this theorem, it's sort of this theorem in this case. And if you just run through the proof, it works. So here's the fact. If a sigma ideal in the space of subshifts to the n to the gamma is, yeah, this is more logic than I intended. Okay, so if it's F sigma hard, then it's pi1 hard. That's the, yeah, okay. So okay, so I apologize. I realize this is not fun. So okay, so the point is I want to show that this. So basically, what this theorem says is that there's sort of two types of ideals. So this is a drawing which I just invented right now. So there's ideals, and they can either be a G delta, or they can be like bad, like not Borel. So they can be sort of these pi1 hard ones. Actually, not Borel is enough. I really need at least pi1 hard. Okay, so I want to show that this. Okay, so first of all, this is an ideal. I should have said. So if you take a union of hyperfinite equivalence relations, a countable union, it's still hyperfinite. I just mean like if you have a space.
Measure hyper.
Yeah, but no, I don't mean increasing. I don't mean the equivalence relations are increasing. I'm just taking if you take a bunch of sub-equivalence relations and union the domains together, then you can get, yeah. So it is a sigma ideal. Also, it's closed downwards, and also freeness is fine. So this is a sigma ideal, and if you define that in the proper way. So if I want to show that this is G delta, I just have to show. So by this theorem, it's either G delta or it's like crazy, and it's not crazy because. Okay, so sketch is that this is, so this condition is sort of equivalent to something called topological immutability. There's a notion of, so an action is topologically immutable if there's a continuous map to probability measures which does something. So that's the topological part. It's the continuous map. So this is equivalent to something called topological immutability for free actions. So normally you need some condition on the stabilizers, but it's free. So okay. This is equivalent. Yeah, for free actions. So it's for free actions, measure hyperfiniteness and topological immutability are equivalent. And this is what's called sigma 1,1. So you can show that the set of things satisfying this property is an image of a Borel set. And because of that, it's not pi 1,1 hard. Yeah, so that's your daily dose of logic.
No, this is for all defined with for all. You have to check something for all measures, blah blah blah. And topological is there exists something. So you swap with for all with there exists, and then your theorem says things are with there exists have to be G delta.
Yeah, and then the equivalence between these is like Han Banach. Okay, well anyway, so this is a dense G delta. It just makes sense, it's easy. You just product with something and then you get that. Okay, so that's nice, but what we really want is so maybe I should have prefaced this with it's a big open question for everyone who's not a measured group theorist, that whether hyperfiniteness and measured hyperfiniteness are the exact same thing or not. So it could be that there's some equivalence relation where anytime you throw away a measure zero set for any measure, it's hyperfinite, but the actual thing isn't hyperfinite, which I suspect to be the case, but I can't prove it because it's hard. So Okay, so the point is you just want to, so showing this is measure hyperfinite is not as good as showing it's hyperfinite. So this is what I want to do. And so we did it. Okay, so that's the theorem. Well, that's a theorem. Those are theorems. Yeah. Okay, so yeah, maybe I should have prefaced this by saying, like if you take F2, it has lots of not hyperfinite actions, right? So maybe you would expect the generic action to be not hyperfinite. But it is hyperfinite, and maybe something that would make you feel better is that it's really easy to see, like without doing anything, that the generic action doesn't support any invariant probability measures. So you would sort of expect maybe there's something going on, like maybe it looks like the boundary action or something. Okay, so that theorem is here, and then this next theorem is here. Okay, so theorem is that the set of S in the space of subshifts, where S is hyperfinite, is cometer. So it's generic. So almost everything is hyperfinite, which is not a surprise because, well, I don't know, Andrew wanted this to not be true so that you could, if you showed this wasn't cometer, you would instantly construct one of these that wasn't these, right? And that would be great. But it's like the quote in the Quanta article where it's like before you prove anything, like anything is possible. But then we proved it, so now this like strategy isn't possible. So okay. No, by the way, go read the Quanta article. Okay. So yeah, so we show this as cometer, and so the way we show this is we don't show this. So there's a theorem. Now this is due to Mike Hochman, and this is a very cool result. So you might be telling me, oh, I don't care about subshifts of the Hilbert. I've never taken the alphabet. My alphabet is like 26 letters or whatever. So there's a theorem that says that generic properties in this situation are equivalent to generic properties in a completely different situation. So this is the theorem. So this is for any countable group gamma. So let P be a property, and by property I mean it's invariant under like topological isomorphism. So let P be a property of compact gamma spaces. These are called gamma flows. So compact gamma spaces. Then the following are equivalent. Do I have like 25 minutes or 30 minutes or what's or how many? Not starting now. Yeah. Oh yeah. Okay, that's a good number. So then the following are equivalent. Okay. So and this is just a nice theorem. So even if you don't care about any of this, just you should use this one. This one's nice. And it's kind of strange. So it says that genericity in one context is the same as another. And for some reason, sometimes it's easier to work in one setting and sometimes it's easier to work in the other setting. That's odd. Okay, so the following are equivalent. So one is that the set of S in the shift space, Yeah, I need a more compact notation for this. So S satisfies P. So you can just take P to be being hyperfinite or something. So this is comeager.
What's a gamma space?
Oh, it's just like a compact space equipped with a gamma action. Space equipped with a continuous gamma action. So, for example, such a property could be like being a free action, or the equivalence relation being hyperfinite, and then by property I mean it's invariant under isomorphism of compact gamma spaces for the notion of that. Okay, so the one thing is that this is comeager, and then the other thing is that some completely different thing is comeager. So it's the set of actions. Maybe I'll call it. I'll do this. It's like Robin. Robin likes this one, right? The actions. No.
I definitely use that.
Yeah. Well.
Dr. W.
Oh, yeah, I like that. So, okay, so the set of actions, which are okay, so it's the following. So it's the homomorphisms from. So it sounds like the actions of the Cantor space on the Cantor space that satisfy this property is comeager. So the action, and by the action satisfying it, I mean again that the equivalence relation satisfies it. Okay, so a homomorphism, a group homomorphism from gamma to the homeomorphism group is just a continuous action on Cantor space, and there is a like a nice Polish topology on it. You just take this to the gamma and you take the things which are homomorphisms. So these two are equivalent. So if I want to show hyperfiniteness, I actually just need to show it in this case. And okay, let me explain in the last, I don't know how many minutes, that why home hyperfiniteness is comeager here.
I'm wondering this is it part of the theorem that one of these sets is bare measurable if and only if the other one is?
I believe so. Yeah.
Okay.
Yeah. It's that basically like this space times something is sort of like bare measurably in an appropriate sense like comeagerly equivalent to this one. Yeah. So yeah.
On the top, you have a connected space. On the bottom, the space is the compact space is not connected. So this is a property of compact gamma space. So what do you mean by property of compact gamma space?
But the subshifts here don't have to be connected, right?
Oh, I see. Okay.
Yeah. So that exactly means that connectedness of the shift is like a meager property here, I guess. Yeah. Yeah, because nothing here is. Yeah. Okay. So yeah. So here's the deal. So actually, okay. So this is what we actually show. The set of actions. Okay. Now I'm going to start using Fn. So this is finite. So the A is hyperfinite, or sorry, A. Yeah, is hyperfinite. Well, okay. So okay, let me say this. A factors onto the boundary action is comeager. So the boundary action is one such action, right? And then so almost everything factors onto this action. And okay, in a couple of ways, the reason we can do this, especially for the free group, is because actually up to isomorphism, there is only one action on the free group. So this is indeed Kwiatkowska. So up to conjugacy, I mean, there's I don't know what I should say. There's a comeager orbit, comeager conjugacy class. Okay, and then so it's not enough to actually know this because so she constructs one with what's called projective price A theory, and to get that it factors onto it, you actually have to look at which like structures she used, and then show that like these things fall into that category of structures, and then you'll get that it factors onto here. And you might be concerned about there's no like a non-free part, but you can just sort of get the hyperfiniteness directly, and you can actually get that it has Borel asymptotic dimension 1. And okay, and if I want to get hyperfiniteness for F infinity, which we can also do, you just show that each of these has Borel asymptotic dimension 1, and then you just take the limit, and that also has Borel asymptotic dimension 1. Okay, so I'm out of time. So.
So you use this Kechris low wooden just to show that this thing is G delta.
Mm-hmm.
Is it obvious distance?
Yeah, density is just because you can if you okay, it's not obvious the way I said it. So if you take an immutable thing and you multiply it by another thing, it's still immutable. And then anytime you can like product something, it's obviously dense because sort of you're only looking at finitely many coordinates, and you can just product it onto some coordinates you don't see.
I guess maybe I didn't catch that. So you get that that's G delta that set. I guess it's on the blackboard behind is G delta. Yeah, I
this one.
understand that. That's what you said, G delta.
Yeah, because it's sigma 1, 1.
So do you have an explicit? Can you write down an explicit G delta definition in the end?
No.
Oh,
Yeah.
What is this black magic?
yeah, but maybe I don't know.
No, because I mean
Interesting.
because you have to show you have to use the fact that not being F sigma hard is G delta, and then you have to go through this wage game, right?
Yeah,
Yeah. So unless you want to do that, yeah.
Borel determinacy is involved.
Oh yeah, that's nice. Oh yeah.
Can you play the same games to bound the complexity of the three hyperfiniteness to measure hyperfinite? Complexity of that set, not
No. I mean, so no, I can no. So basically, this just finds like so in the Cantor space case, you actually show that it has dense interior, so it has an open dense like subset where something happens, but we can't like characterize the hyperfiniteness at all.
But I guess what I'm saying is if that set is not G delta, then you've done something, right?
Oh yeah, that's. Oh no. So this one we know it's we still know it's like sigma 1 or pi 1, 1 hard or something. I guess. Yeah. Yeah. Oh yeah. But you know, it could be sigma 1, 2 hard or something. Yeah.
Thank you.
Yeah.